Hello everyone, I am Teacher Wells and today we are joined by Teacher Raphy and Teacher Kari for this explainer on what makes teaching magnetic fields a challenging task and how we can improve it. Teaching magnetic fields to high school and college students can be a challenging task as it involves abstract concepts that are not directly observable in everyday life. However, it is a fundamental topic in physics and plays a crucial role in understanding electromagnetism and various real-world applications. As physics teachers, you may encounter students who struggle to grasp the underlying principles of magnetic fields, making it essential to employ effective teaching methods to enhance their understanding and problem-solving skills. One study that reported positive results in teaching magnetic fields used drawing representations of magnetic force lines and magnetic poles. The researchers found that incorporating multiple representations helps students better conceptualize the complex nature of magnetic fields and interactions between magnetic poles. Additionally, the study showed that integrating mathematical representations alongside the visual drawings further reinforced students' comprehension and problem-solving abilities in magnetic field topics. Another study implemented online problem-based learning assisted by digital books embedded with 3D animation to improve students' physics problem-solving skills on magnetic field subjects. The researchers found that interactive 3D animations allowed students to explore magnetic field concepts visually, enabling them to form a better mental model of the phenomena. The problem-based learning approach facilitated critical thinking and encouraged students to apply their knowledge to solve real-world physics problems involving magnetic fields. One fundamental concept in magnetic fields is the Lorentz force. It explains the interaction between charged particles and magnetic fields. The Lorentz force describes the force experienced by a charged particle when it moves through a magnetic field. And to aid visualization, we can use this GeoGebra simulation with the link in the description, or this animation by Walter Febb, or these collections of YouTube videos by the T3 framework. Again, links are provided in the description of this video. Another concept is the Vesobart law. It describes the magnetic field produced by a steady current in a wire. And we can use this VSOBAR calculator with embedded animation, or this animation again from GeoGebra. First, we cannot stop at just providing for visualization. We also need to cover for the mathematical skills, and for that, we have Teacher Rafi for the Lorentz force and Teacher Kari for the VSOBAR law.
Hi, I'm Sir Raphy. Thank you very much, Sir Wells, for presenting to us how we could improve teaching magnetic fields in high school and college physics. Now, allow me to present a solved problem related to Lorentz force. This is for high school physics. We now have your problem. The problem reads, consider an electron moving with a velocity of 5.8 times 10 to the fourth meters per second in magnetic and electric fields with intensities of 1.9 times 10 to the negative 3 Tesla and 1.2 times 10 to the negative 3 volt per meter respectively. The path of the electron is making an angle of 30 degrees with the direction of the magnetic field. Determine the magnitude of the Lorentz force exerted on the electron due to the interaction with the electromagnetic fields. We can present our given here. We now have your velocity v, which is equal to 5.8 times 10 to the fourth meters per second. We also have your magnetic field b, the magnitude of such 1.9 times 10 to the negative 3 Tesla. We also have your electric field E, magnitude of such 1.2 times 10 to the negative 3 volt per meter. And then we also have your theta, or the angle, which is equal to 30 degrees. And then our Q, which is the charge of the electron, 1.6 times 10 to the negative 19 coulomb. We can have our sketch. Okay, take note that Lorentz force, as we all know, is the sum of your electric force brought about by the electric fields and the magnetic force brought about by your magnetic field. And in this case, you have here a moving electron 30 degrees in the direction of your magnetic field. In this case, we are considering the electric force, so you have a representation here of your electric field shown by the different arrows. And take note, your electric force is given by the product of the charge of your particle, in this case, charge of the electron, times the magnitude of your electric field E. We can have another sketch. This time, instead of your electric field, we now have your magnetic field B, and then the same, but of course, we should expect that the electron will now move in a circular path. FB now, which is the force, magnetic force to be specific, is equal to the product of your charge of the particle, in this case, charge of the electron, times the cross product of velocity V and your magnitude of your um, magnetic field B, big letter B. We can now present our solution. Take note of the equation for the Lorentz force. This is the sum of your electric force, which is given by the product of your charge of the electron Q times the magnitude of your electric field. And then this is your magnetic force, which is the product of four quantities: the charge of the particle or charge of the electron Q times the magnitude of the velocity V, and then the magnitude of your magnetic field B, and then the sine of theta, where theta is 30 degrees, and as we all know, sine 30 degrees is 0.5 or 1/2. By plugging in the values as shown in the given earlier, we can have our substitution. And this is presented here. And we will end up with a final answer, which is 8.8 times 10 to the negative 18 coulomb, which is now the Lorentz force exerted on the electron due to the interaction with the electromagnetic fields. Thank you. The next would be the presentation of a solved problem by Maám Karizza.
Hey there, fellow science enthusiasts. This is Teacher Kai. We were introduced with a rough idea of the formula of Biot-Savart law by Teacher Wells. Now, let's solve a problem. To make things simpler and clearer, let's work through a simple problem. Imagine we have a short wire of length 1 centimeter carries a current of 2 amperes in vertical direction, as you can see in the figure. The rest of the wire is shielded so it does not add to the magnetic field produced by the wire. Let's calculate the magnetic field at point P, which is 1 meter from the wire in the x direction. Let's recall the quantities given. We have the length of wire, which is 1 centimeter, as you can see here, current of 2 amperes, and distance from wire to P in the x direction, which is 1 meter. What we are looking for is the magnetic field at point P. We can determine the magnetic field at point P using the Biot-Savart law with the following formula. Since the current segment is much smaller than distance x, we can drop the integral from the expression. The integration is converted back into a summation, but only for a small dl, which we now write as delta L. Another way to think about it is that each of the reduced values is nearly the same, no matter where the current element is on the line segment, if delta L is small compared to x. Therefore, our new formula is the angle theta is calculated using a tangent function. Using the numbers given, we can calculate the magnetic field at P. The angle between delta L and vector r is calculated from trigonometry, knowing the distances L and x from the problem. Therefore, we have an angle of 89.4 degrees. Now, plug in the given values to the formula. And we have the following result. From the right-hand rule and the Biot-Savart law, the field is directed into the page. This approximation is only good if the length of the line segment is very small compared to the distance from the current element to the point. If not, the integral form of the Biot-Savart law must be used over the entire line segment to calculate the magnetic field. Awesome! We've successfully applied the Biot-Savart law to find the magnetic field. Remember, practice makes perfect, so don't hesitate to try more problems to master this concept. And there you have it, the Lorentz force and Biot-Savart law demystified, and some problem-solving examples to reinforce your understanding. Electromagnetism is truly fascinating, and the applications of this law are vast. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more exciting science content. Until next time, keep exploring and stay curious.